Hello, this is the demo for uh, the Scholar PyTorch neural networks tutorial. So this is the how we will use PyTorch for neural networks. So in the previous notebook, we built neural networks from scratch with NumPy, but now we'll do that with the PyTorch, and as we know that um, the framework that empowers cutting edge AI research at Meta, Tesla, OpenAI, and beyond. So why PyTorch is it has automatic differentiation, whereas in NumPy it is manual implementation. So PyTorch has it built in. CPU acceleration is not supported in NumPy, but it is there in PyTorch. Dynamic computation graphs. NumPy doesn't support that, but PyTorch It does. Production deployment is very limited, but in PyTorch we can, it supports TorchScript and ONNX. Yeah, so that is. So in this we'll first cover the PyTorch fundamentals, Einstein's summations, autograd magic, which is automatic differentiation, computation graphs, and we'll build a neural network using only basic PyTorch operations. Then we'll go to higher level integration using NN model NN.linear and the other optimizers, using of data loaders, training loops, and the best practices. So initially we are just initializing the libraries and finding out the GPU and setting up the GPU, etc. Then it's the let me just yeah so creating tensors, as we have discussed this in the previous notebooks, that tensors can be created from lists, NumPy arrays. We can have special types of all zeros tensors, all one tensors, random valued tensors, identity metrics, uh, yeah and we can do several operations on top of it. So now the data types we have: float 32, float 64, 16, um, brain float 16, integer 64, boolean, like that. And these are the sizes which are used. Then for device, yeah, for CPU, we can use CPU tensor, but we can also use GPU. So GPU is so the best practice is to use CUDA device, so that the computations are really fast. uh, then tensor operations, these are just revising the topics. We can add two tensors, multiply, exponent, divide, square root, find its exponent, etc. We can also do matrix multiplication like this. These are the three equivalents. This is we can use matmul function, we can use this operator, or we can just do mm. And this one is only for 2D arrays. If we have a 3D and a higher dimension, then we have to use these or this. Yeah, these are the other operations supported as well. Then again, reshaping and broadcasting both are available in supported in PyTorch. So for reshape we just have to the tensor dot reshape and its dimension, so it will get this tensor will get transformed into this 4x3 matrix. So that is possible. So let's say when we have to for let's say for matrix multiplication, we have to have the columns of first matrix matching with the rows of the next matrix. That is the condition. So let's say our data is not in that format, and at that time we use this reshape function to get into a particular shape. Then we can remove one dimension out of the tensor. Yeah, adding, removing. So squeeze is removing one dimension, and when we want to add one dimension to it, we can do unsqueeze. Then it also supports Einstein summation. um, so torch.einsum is one of the most powerful functions in pytorch. It can express matrix multiplication, dot products, outer products, transpose, trace, batch operation, and much more. So the notation is like this: Einstein sum, you just uh, each tensor gets subscript letters, and these operations are uh, s- uh, sum on top of it. So in the subscripts, we'll see how we can write the subscript. It's mostly like this. So it basically defines what operations you want to apply on the matrices. It should be some example. Yes. So this means some. This is transpose a vector, transpose a matrix. Um, this is row wise sum. This is a diagonal matrix, and then this is trace, like that. So the idea is, instead of you telling the PyTorch do these operations in chain, you can just give this subscript, and it will do the operation for you, and the tensors of course, and it will do the operations on top of it and give you the result. So yeah, that is pretty much it. Then Einsum has batch operations as well. We can find attention scores in this in this format. um, we can also apply softmax and multiply vector v, so that is that can be shown like this. It can be done like this. So yes, yeah, this is the cheat sheet which it has. Now autograd. So this is the magic of automatic differentiation. So you don't have to manually calculate the gradients at each time. So remember implementing backpropagation by hand in NumPy. So type PyTorch autograd does it automatically. So how it works is, it create tensors with requires underscore grade equals to true, grad equals to true, and it performs operations. So PyTorch builds a competition graph automatically, and then when we call backward function on the output, the gradient appears in the dot grad attributes. So it does it in background. You don't have to do it manually like we did in NumPy. So yeah, let me just when we are creating the tensor, we just have to put this requires grad equals to true, and yeah, whenever we call this dot backward, like we did in, I think we did that implementation, we did output dot backward, and yeah, then it creates the it computes the gradient, and that can be accessible using the dot grad attribute. Yeah, so yeah, let me so let's say A is 2 and B is 3, and we are doing the C operation is A cross A multiplied by B, just this, and then we have C, the output which we got, add with A, we get D, then we do D to the power 2 and we get E. So the gradient of D by A will be it will be a chain thing, kind of a thing. Okay, how much chain uh, mm, what do we say, D by uh, DE by DD. DD can be DE by DC, like that. It back propagates, and like we did in the I don't want to explain because I have already did that. So that computation is how it looks right now. Now let me mm, yeah, so here we are just printing after one backward call what was the gradient value, and you can see the gradient value is getting increased over time as the run is increasing. So though yeah, so what we want is so after every epoch we have to reset our gradients because the values are stored, because we have put it as requires grad equals to true. So every time the grads are not initialized again, but they are the same. So what we have to do to avoid this, because then it will not be true, right? The values will be not be true. So what we have to do is we have to set the gradients to 0. That's why we do that dot grad equals to 0, some 0 grad, some function was there, I forgot. Yeah, yeah, we can do this y underscore detached equals to request grad equals to false, or we can do this torch dot no grad. So what it does is it automatically sets the this grad requires grad equals to false, so that it is the gradients are released from the memory, they are not in use. There's one more step to it. There's one more method to do that, and that is grad 0 something. When we are calling, when the optimizer, we just do optimizer dot 0 underscore grad thing that we will cover in the more advanced notebooks, but yeah. So the idea is to always find the global minima, and because that is where we will get the minimum loss and most accurate values. So that is why we find the gradient descent. Now let's implement a neural network from scratch, and again, very basic pytorch operation. We are not using the module yet. Yeah, so we define the activation functions based on their formulas. Then we create input and after the sigmoid, after ReLU, after leaky ReLU, how the output looks. Then for loss functions, we are defining our loss functions ourselves, which is MSE loss for a regression problem, binary cross entropy for binary classification, categorical cross entropy for multi-class classification problem. And we are just the whatever predicted value we got, we'll just pass it through the y predict and to predict to MSE scores and MSE loss and binary cross entropy loss, and we can see the values here. Now let's build the neural network from scratch, as we have defined the major things outside. Let's say this is the neural network class, primitive class, which we are using basic operations. So what we will initialize is first as the layer size and the activation we want to use, and whatever the this value it uses, it will take that particular function, activation function. Once that is done, then we have weights and biases initialized, and now based on like how many layers we want, we will we will create what are the input values and what are the output values, and based on the input and output value, we will create the weight matrix and bias. Once that is done, we will, for both, we will make the gradient true, because we want both these values to be, to be changed as for the minimum loss. So then we will just append the weights and biases to those. Once the initialization is done in the forward, we want to call the layers in the sequence. So here what we will do is, for each weight, we want to, for each layer we want to do the linear transformation, which is this x, the input matrix multiplied with weight matrix, and then we have to add the bias. So that is what is happening over here. And then once that is done, we want to pass it through the activation function, and we'll get the output. And excuse me. And for output layer, we don't want any no activation for now, so we'll just keep it as is, no activation function before the output layer. Once that is done, we'll just return the outputs. And here these are the parameters which on which we want to train, which is weights and biases. So then this zero grad is to set the gradient to 0 before each epoch. So yeah, then we are fitting the model. For fit, we want our x, y, and how many epochs, learning rate, what loss function, like that. So once we get that, we just setting up the what loss function we will use. Once that is done, we are creating that loss function as a compute loss, and for each epoch we'll run that self.forward. So it will run the layer and it will give us the predicted y value, and using that we will find the loss. Once the loss is found, we will do the grad underscore 0 to clear old gradients, and then we'll do this compute new grads. So it will create the new gradients based on the loss and the predicted values, and once that is done, the values will get changed. Excuse me. Now gradient descent update we'll do this is to release the gradients which we had done earlier. Basically turn off the gradient tracking. It saves memory and speeds up things. So once that is done, we are calculating our accuracy, and the other matrix we will calculate, and we'll just return the history. And that this was fit. That's basically fit the model. Now for prediction, what we want is, we want to call the forward and get the output, whatever prediction we got. So we'll just see. So for XOR problem, as we saw in the earlier videos as well, that XOR is a non-linear operation, and using statistical model, very basic neural, even a single neuron was not able to solve the XOR problems. We need more neurons and layers to extract the non-linearity, to figure out the non-linearity, and it worked well. So we will just test it over here. So here you can see that we have layer 1 and layer 2, and we had total 33 parameters, and here we use the activation as tan, and we had 1000 epochs, and after each 100 epoch we got the accuracy, because each neuron was able to extract one feature out of it. And so you can see that it the loss nearly went down to 0, and it worked really well. Now let's create the neural network using the NN model of the pytorch. So in that, in this case, the earlier case, we did create everything on our own, which is, which gives more control to us. But let's say we want to use a very generic model again and again, no, like, and so, and you don't want much control in your end because you are going to do something very generic, then it is best to go with the NN module. So you just have to, will inherit from NN module, and we'll just create a layer. So yes, so NN dot linear is just a linear layer. It will create a fully connected layer, and yeah. So let's see how it works. We have to give the weights shape bias shape, and yeah, how they look. So these are the tensors. Now we have to create a very simple neural network. So in this, basically we have created a tensors of input and output, how they look, the weights and everything. Here what we are doing is yeah, we are inheriting the properties of NN dot module, which helps us create a very simple neural network, and the forward, the other things, and are taken care over here, so we don't have to compute it. So when we initialize, we just do this so basically it is calling the parents initialization function, and this is very important to do. Now we'll define our layer. So we want a linear layer, which is the first layer, and the size should be input size and the hidden size. Then we have a second layer, which is hidden size and output size, and the last layer this value should always be equals to what the output size is. So then we are setting the activation function. Then in the forward, we are just calling the layer, so how we want it. So we are just calling cf1, then we'll call relu, and then we'll call cf2, and just return whatever value we got. So it's as simple as that. Then when we just defined our model, we instantiated our model. Now for yeah, it is just printing that. Yeah, here you can see the, so NN linear is basically a very simple, fully connected layer. We can also have NN dot sequential. So here what we did is, we called each and every layer and activation function one by one, and if it is most of the time going to be sequential layer. So what we can do is, in a very simple term, we just call NN dot sequential and pass the layer NN dot layer, the size of the layer, activation function, again another layer, activation function there, and another activation function, like that, at sequential. So it's easy to use. You don't have to do a lot of things in your thing, and yeah, that is. You can create a multi-layer perceptron with the given architecture. You just how many layer sizes and these things, and it will give you, the NN dot sequential of those particular layers. So it is quite easy to use. Now let's create a complete neural network class. So in the neural network, what we are again inheriting from the NN dot module, we are initializing the layers, activation, dropout, batch norm, etc. Setting up the activation function, initializing, and in the forward what you want to do. Once that is done, we are just creating the network. We just created our model. Once that is done, we will call these optimizers. So optimizers are basically the gradient calculators which pytorch inbuilt has. So this SDG is stochastic gradient. Then we have this Adam mostly used, and you have to pass the model dot parameters and the learning rate to it. So yeah, once these are the available optimizers in pytorch. Once that is done, in the training module, we just pass these values um, x train, y train, x value, y value. These are the predicted values, and what the learning rate should be, loss function, or what optimizer, etc. like that. Once that is done, let me just go to the, yeah, the here we are just creating this. So we have this data loader thing. Data loader is basically for more uh, so it automatically creates batches and shuffles the data after each epoch, so you don't have to take care of that. So yeah, it also helps for parallel processing as well. So yeah, that is additional functionality we have. Then we are doing this, yeah, for each epoch, x batch and y batch, batches will be created out of data, and we will create y, we will take y value or y predicted values, we will find the loss, we will clear the gradients first, then compute the gradients, and this optimizer dot step is where we update the weights based on the gradients. So once that is done, for each value again the data loader will shuffle the data, and then it will go through the neural network, and the gradients will be calculated like that. For each epoch that will happen, and we will get the values. So yeah, that is pretty much it in this. I think this also explains the, yeah, so here you can see that it's such a complex data, and still it is able to find out the boundaries, like we did in the Amsterdam and Belgian border as well. So these are some functionalities of neural network, which is it is able to find out such complex patterns out of data, which even with the naked eye we cannot find out, of course, because of the high dimensional data. So yes, thank you.